as an application of change of basis, we'll see how to render an image with perspective. So we're going to use the same math in the next lab, where instead of adding perspective, we'll take some away. So we start with the points making up a wireframe cube. Now, and we're going to move them. We're going to translate them for reasons that will become apparent later. So we'll move them over. Now, how does a camera or an eye see these points? So we have to start talking about cameras. So here's a simplified model of a camera called a pinhole model. There's a box with a hole here, and the light from the scene goes into the camera through the hole and hits the back of the box. Now, a photon only gets into the box if it goes through the hole. So the only photons that hit the back are those that go straight through the hole. The hole is called the camera center. And in the back of the box, there's an image sensor array. That's what detects the photons. Okay, so when the photons bounce off the scene and pass through the pinhole and strike the image sensor, the camera registers them. And as you can see, the image ends up being inverted. So there's an even simpler model in which we get rid of the inversion. This simpler model is used to avoid the inversion of the image. In this model, the image sensor array is placed between the camera center and the scene. And the plane containing the image sensor array is called the image plane. And a photon is detected only when it goes right to the camera center. So it has to bounce off something in the scene and head through the image plane to the camera center to be detected by the sensor array. And which sensor array element detects that photon? It's whichever sensor array is intersected by the line that the photon travels along from the scene to the camera center. So we need a way to map between points in the world, P, and the corresponding points, Q, in the image plane. And we're going to do that using a specially designed basis, which I'll call the camera-oriented basis. The origin is defined to be the camera center. That's why we had to translate that wireframe cube to get it somewhat away from the camera center, the origin. The first vector in the basis goes horizontally, and I'm just going to make it the length of a pixel, the length of a sensor element in the sensor array. The second vector in the basis goes vertically, the length of a sensor element. And the third vector goes from the origin to, say, the top left corner of the sensor array. Now we'll see why the camera basis makes it easy to perform this transformation. So here's a side view where we don't see A1 because it's pointed directly at us. But we do see A3 and A2. And here's the scene. And there's a point P in the world. So first, let's express that point in terms of A1, A2, and A3, the camera basis. So we get the coordinates of that point. Let's call them x1, x2, x3. And notice that the point is then the linear combination of A1, A2, and A3 given with these coefficients. x1 times A1 plus x2 times A2 plus x3 times A3. And we only show x2 times A2 plus x3 times A3 because x1 times A1 is pointed directly towards us, because we have the side view. Now, and how do we go from the point P to the point Q? We use similar triangles. So here's some big triangle. And this is a little triangle. The point P corresponds to point Q. The coordinates of point P are x1, x2, and x3. What are the coordinates of point Q, we know that the third coordinate, x3, is 1 because this point lies in the image plane. To get from x3, a3 to a3, we divide by x3. But by similar triangles, we have to divide all the coordinates. So the coordinates of this point are obtained by dividing all the coordinates of this point by x3. So its coordinates are x1 over x3, x2 over x3, and x3 over x3, which, of course, is 1. So to summarize what we've discovered, given the coordinates x1, x2, x3, in terms of the camera basis, a1, a2, a3, of a point in the scene, we find the coordinate representation of the corresponding point in the image plane by just dividing all these coordinates by x3. We get x1 over x3, x2 over x3, and x3 over x3, which is always 1. So I'll call this scaling down. Now, once we have a point in the image plane, it's pretty easy to find out which sensor element it corresponds to. Let's say the point has coordinates x1, x2, x3 with respect to the camera basis. Then all we have to do is drop that third coordinate. After all, it's always equal to 1. And because of the way we've constructed this camera basis, that tells us the coordinates within the sensor array of the particular sensor element that Q lies in. To go from the coordinates of the points making up the wireframe cube to the pixel coordinates, we go through the following process. First, we write the basis vectors of the camera coordinate system using the world coordinates, the coordinates with which we've written the points of the wireframe cube. Now, for each point P in the wireframe cube, we find its representation in terms of the camera basis. We scale down, that is, divide by the third coordinate, to get the corresponding point in the image plane, and then we convert to pixel coordinates by dropping the third entry.
Here's the camera arrangement I'm going to use. The camera center is at the origin. This square is the image sensor array, and here's the wireframe cube we're going to view. When light goes from the wireframe cube directly in a straight line to the camera sensor, if it intersects the sensor array, then the sensor element at the intersection point picks up that light. The camera will have a view that's closer to this. Once again, here's the camera arrangement. The first thing we're going to do is construct the camera basis. Here's a diagram showing the vectors of the camera basis. The image sensor array is 1 by 1. Here's a view with the z-axis going straight into the screen. So the first vector, A1, has a length that's that of a single pixel. This is 1 over 100. And it goes in the direction of the x-axis. The second vector has the same length, goes in the direction of the y-axis. And the third vector goes from the origin to the top left corner of the sensor array, which looks like it should be at minus 1/2, minus 1/2, 1. Let's look at the result. And this is the coordinate representation for this point way out in the scene. What we want to do is find the corresponding point in the image plane, and we do that by dividing by the third coordinate, 8 in this case. And this gives us the location in the sensor array. So the pixel coordinates are 62.5, 62.5. Now we can plot this. Now we're ready to try the same thing with the whole wireframe. We use a procedure that gives us line segments. And now we take the corners of the wireframe cube, suitably translated, and construct the line segments with the given corners. Now we put together all those lists to get the set of points that we want to render. Now, the first step in rendering these points is to find their coordinate representations in the camera coordinate system. Next, we have to find the corresponding points in the image plane. We do that by scaling down by the third coordinate. And here we'll derive those points. Now, from these, we want to find the pixel coordinates. I'll define a procedure to do that. It just takes the first and second entry. And now we derive all those pixel coordinates, and we can plot the points. I want to draw your attention to one step in this process, finding the coordinate representation of the cube points with respect to the camera basis. We used vector rep, but we could have done it using matrix multiplication. Here's the matrix whose columns are the vectors of the camera basis. If we were to multiply this matrix by the coordinate representation of a point in terms of the camera basis, we would get back the point represented in world coordinates. To go the other way, from world coordinates to camera coordinates, we use the matrix inverse. First, I'll import a procedure for finding the matrix inverse. You'll write this procedure later. Although you could have found this inverse just by hand. Now, we can get the coordinate representations with respect to the camera coordinates of all the points making up the cube by multiplying them by this matrix inverse. For example, here are the coordinates of the first point on the list.